2 divided by 3.
Well, if you have 2 oranges to split amongst 3 people, how much of the orange does each person get? 2/3. And so that's splitting 2
Pay attention. You have attention.
2 evenly. And so the 2 oranges have the negative charge.
Yes, yes.
So we have 2 negative charges split amongst 3. That means each oxygen in the hybrid gets
2/3.
2/3 of the charge. In the hybrid. The hybrid.
In the
spread.
hybrid.
Yeah.
Oh, okay.
That's
Because
where the
it's
2/3.
It's all over.
Yeah, what you do is you just spread out the electron cloud like a fog over the 3. I showed it. How did I show it spread out over
Okay.
3?
Thank you so much.
But yeah, I didn't. To show it spread out, I represented lone pair like this.
Pay attention.
And so we're going to spread out the negative charge over all 3 now. And so each oxygen comes out negative 2/3. And so this lone pair, there are 2, one here, and none here. Now those 2 lone pairs are going to be spread out over 3. So this is why I drew this kind of dot, these dots, dash, whatever, to show it's being smeared out over 3, the electron cloud. Does that make sense? Okay, that's fine. I saw this just before class, so I thought that was pretty good. There's lots of animations. S orbital, px orbital, py orbital, pz orbital. And so here you have your unhybridized p orbitals and s orbitals. And so we can mix them. We mix one s and one p, we get sp hybridization. So we generate these 2 new orbitals shown here. And then we still have the py and pz unhybridized. This coordinate system is different from before. It looks at it slightly, but it doesn't matter what the coordinate system is.
What is this website?
LearnersTV.com. Just search animation of orbital hybridization. This will come up there. And so here, we take 2 of the p's now and hybridize it, and we generate b's. What are the blue orbitals called? sp2. And what's the green orbital? That's the unhybridized p orbital. sp2. 3 sp2 orbitals shown here, and 1 unhybridized p orbital shown here in the middle. And then we have what, sp3. Let's take a look. sp3, there are no more p orbitals left. This is the sp3. Got to point the camera to that. So just quick for the camera. The S, px, py, pz, they're all superimposed on each other. SP hybridization. sp2 hybridization. sp3 hybridization. This is one of the animations. There are more, This one's only uploaded a year ago.
Orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The 3 p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce 2 hybrid orbitals called sp pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all three p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
Okay. So that's the
Let's apply the concept of hybridization to ammonia.
Actually, we already did
Here is
that.
the Lewis structure for ammonia.
There's lots online. So let's go back to what we were talking about earlier, which is molecular orbital theory. So there you saw the mixing of orbitals on the same atom. You know, you take an s orbital and a p orbital on the same atom and mix them to get 2 new orbitals. This forming MOs is similar, except we're mixing the atomic orbitals on 2 separate atoms. So we mix an atomic orbital on atom A and an atomic orbital on atom B together to get these. This is called what? LCAO, which stands for
Linear
Combination of atomic
combination of atomic
yeah.
orbitals.
And this is our linear combination of atomic orbitals here. Here we do it in phase here. It's a bonding orbital. Out of phase, we give you a anti-bonding. So we do it both ways, and we generate 2 new orbitals. These are molecular orbitals here. They form from the atomic orbitals here. These dashed lines just represent the linear combination of the atomic orbitals here. So this is our first period. And then we had it for second period, which gets a little bit more complicated. So let's take a look at these here. And so if we take a px and a px, mix it in phase, to the positive amplitude here, constructed here, we grow this bigger. And the 2 blues out. And this is the sigma 2p. However, if we do positive amplitude, negative amplitude, is going to, no, we get this construction. And so this is the out of phase one. And so this is the anti-bonding. So for every bonding, we also form an anti-bonding depending on how we mix it. The same thing here. Rather than going head on, we go side on. So we bring these together here. The blue and the blue, the red and the red. Match in phase.
Question. What do you mean by positive and negative amplitude?
Positive and negative amplitude is the wave function. What I mean is this. Here, this is positive amplitude here, this is negative amplitude. Now, this is standing wave, so let's get it. All right. Here's the wave function. Oh, shoot. I don't remember where it was exactly. Where was it? Do you remember the drawings I did? Maybe it's just quicker just to draw and look at them. What does a P side 2P look like? Can somebody draw a side 2P? I don't know how many times I drew it in class, a bunch of times. Does this look familiar?
Yeah.
This is the side 2P wave function. This is positive amplitude, this is negative amplitude. But we don't look at side 2Ps, we look at psi squared, so we lose the what we call phase information, so we do psi squared. When we do psi squared, then it all looks positive amplitude, but it isn't really all. You know, psi squared is going to be positive, but there's phase information that's lost. If you take the square root of 4, you know, the square root of 4, is it plus 2, minus 2, plus minus 2? What is it?
Plus minus.
You don't know, right? You've lost the phase information. In mathematics, though, you don't want to lose the phase information. And so what people do is they carry the phase information along with them so they don't lose it. This happens a lot in science where you do a square root or you square something. When you square something, you don't want to lose that information, so you carry it with you.
Why do we square it instead of just keeping it, keep the information like that?
Because people hate negative probabilities. What is a negative probability? It makes no sense to have a negative probability, so they don't do that. You know, we should just keep it like this and just realize that the negative should be, what the negative means is it should just be the absolute value. Then no problem, you know. But anyway, psi squared, there's another reason. Psi squared is directly related to probability. That's the other thing. I don't know, mathematically there could be something in there where it's a square. Well, what does Petrucci do to not lose the phase information? He colors this one. This was supposed to be blue. All these pens are supposed to be caps. It was, he colors one what? Yeah. He colors the positive low, blue, and the negative low, red. Now, when we form bonds, right? When we form bonds, the phase information is so important because when we form a bond, in valence bond theory, when we form a bond, what happens? We overlap atomic orbitals. Now, how are you going to overlap it? You know, well, even though psi squared's like this, it's always positive. That's not the case because what we're overlapping are the wave functions here. And we can either overlap it constructively, that is, going back to this. With the positive amplitude with the positive amplitude, or we could overlap it with the positive amplitude with the negative. The positive and negative, they're not going to overlap, right? They're going to cancel each other out. So that would be antibonding. And so when we mix the wave functions, or this is for valence bond, when we overlap the wave functions in valence bond, we got to pay attention to this. You know? Also, when we mix it, you know, for hybrid orbitals, the same thing happens. I didn't really talk about that little lobe, you know, why the actually I'm not going to talk about it. You know, but it's important. And then in MO theory, this is very important because, you know, we're doing a linear combination. Linear combination, we got to look at the two possible ways of adding it. We add it with the positive amplitude and the positive amplitude matching, or we add it with the positive amplitude and flip the other one, so the negative amplitude. Do you see that? That's a linear combination, the two possibilities. And so we generate two possible MOs. All right, does that answer your question?
No.
No. No.
Well, no, it's not that. Something steady.
Well, that's all the color coding here. There's other ways, you know, a lot of books don't use color coding. A lot of books will just put a plus symbol in this lobe and a minus symbol in this lobe. In fact, I think most organic books will do that. Plus symbol and a minus symbol. At least mine do. A lot of other general chemistry books, Chem 1A books, will do the plus and minus symbol. Most papers that you read in the literature, plus symbol and a minus symbol, because color coding is very expensive for journals. So they just do it simple. Okay, well anyway, this is generating the MOs. So we generate the sigma 2p, the pi 2p's. These are a whole bunch of new orbitals we got to keep track of. And so here they're shown here. You know, px and px, You're going to get the sigma 2p and the sigma star 2p. The py, we get the pi, you know, where the pi and pi star. Here we're going to get the pi and pi star, 2p orbitals. Let me put these together. Okay, here on the left, these are the molecular orbitals for fluorine. You see them? We have diagrams like this. And so we're talking about this diagram, correct?
Yes.
Yeah, okay. You don't have to show this. Now shows the linear combination of the atomic orbitals. And so we have atomic orbitals on one atom, atom A, with the atomic orbitals on atom B. We do the LCAO. When we do the LCAO, we get the additive, the subtractive here, according to how the book is written. In other words, in phase, out of phase, bonding, anti-bonding. All right, all these orbitals here are the new orbitals of the molecule. And we no longer have, does the 2s and 2p still exist in the molecule? No, those are gone completely. And so in this molecule, no 2s. Did we already do oxygen? O2? Yeah. Okay, so we don't have the 2s and 2p's in oxygen. When it's in the molecule, we just have the sigma 2s, sigma star 2s. Actually, we also have the sigma 1s and the sigma star 1s, but those aren't shown for this example here. All right, so it turns out it's a little bit more complicated because there are two MO. We call these MO, or molecular orbital diagrams, or molecular orbital energy level schemes, or molecular orbital energy diagrams. When we look at this, take a look at what happens here. Compare this to this. Do you see the difference? Especially around here. The difference is what happened to the sigma 2p. It used to be down here, now it got popped up to here. And so why was that? Did I talk about this at all?
No.
Okay, so let's talk about this now.
Can you turn the camera back?
Yeah. Now back to the board here. Okay. So there are different ways that people remember this. One way that some people remember is they remember it based on the LCAO of the atomic orbitals. So, you know, if we have a 2s and a 2s, what are the orbitals that we're going to generate? Okay. The other way is just people just memorize it. You know, you memorize it like 1s, 2s, 2p, actually 2p, what comes next?
3s.
3s, 3p,
4s,
4s, 3d, 4p. So you memorize it. You could do the same thing here. You can just memorize it. Sigma 2s, and then we know sigma star 2s. This is all you need is the blue. But as an aid, some people like to, and I used to like to do this myself, some people like to see where these orbitals come from, so they'll do this. They'll do the 2s goes to a sigma 2s and a sigma star 2s. That would be the LCAO. But we don't have to do that. But when it comes to the 2p's, people screw these up all the time. And so sometimes it's very helpful to do the 2p's like this, because here we should form the sigma 2p, right? Sigma 2p looks like this. And then the sigma star 2p, which will bump up in energy the same amount of this drop in energy. So this is sigma star 2p, which is going to look like this, with a node, you know, down the middle here. Node. That's when the 2p orbitals come head on each other. And then we have the pi's. The two pi's are just going to differ by the plane that they occupy. And so one of the pi 2p's is in the plane, the other is perpendicular to it. And then we have the pi star 2p, pi star 2p here. And those are, and so let's see if this is working a little bit better. And so the in plane, you know, pi 2p might look like this. You know, looks like a pp bond. This other one is going to be perpendicular, so it's going to stick out like this. And the other one should stick in here. And then the pi star 2p, the one in the plane, is going to have the lobes repelling each other. There's a node down here. And then this one will be just twisted into the other plane. Let's see if I have at least some pen here. And so lobe comes out, lobe goes in, lobe comes out. This lobe goes in. There's a node here. These are the orbitals. Okay, when z is big, what tends to happen with big z's? If z is big, then the nuclear charge is, the positive nuclear charge is high, and it tends to pull in the orbitals. And so this is z greater than or equal to 8. And so in other words, z is big. Z is big, that means the electrons get pulled in tightly. Now, let's look at a 2s. A sigma 2s looks like this, right? The sigma star 2s looks like that. And we're going to compare the sigma 2s and the sigma 2p. And so if z is big, which one is more penetrating? A sigma 2s or a sigma 2p?
Sigma 2s.
The sigma 2s is more penetrating. And so when z is big, we get a situation like this, where the sigma 2s is pulled in tightly into the nucleus. Okay. And the sigma 2p's, being less penetrating, are not pulled in as tightly. And so this would be the sigma 2p here. Okay. Whereas when z is small, then this isn't as big of a factor. When z is small, then the electrons aren't pulled in so tightly. And so the 2s is a bit bigger, like this. And so what we see is that the 2s and the 2p pretty much occupy the same space. So this is sigma 2p. This would be the sigma 2s. And so, in other words, this. When the orbitals aren't interfering much with each other, then the electrons have their own space. And so if we have two electrons in the sigma 2s and an electron in the sigma 2p, the sigma 2p has some more room to avoid the 2s electrons. Whereas over here, if we have two electrons in the sigma 2s, then the sigma 2p is pretty much stuck in the same volume here. And so what we get are electron-electron repulsions are more significant. Electron-electron repulsions are more significant. In this case. And then over here, electron-electron repulsions are less significant. And That's because the overlap in space here was the so that means we end up with two diagrams here. When Z is small, we get electron-electron repulsions. The sigma 2p electrons and the sigma 2s electrons interfere with each other here. Repulsion. And what that does is it destabilizes the sigma 2p and puts it higher in energy. So the sigma 2p gets popped up in energy because the repulsions between the 2p and the 2f. Does that make sense? No? Not at all? What?
What does Z stand for?
Z?
Yeah, for proton.
Yeah, number of protons in the nucleus. No, doesn't make sense.
Can you dumb it down a little bit more?
Okay. Looking at these two figures here, which one do you think was going to have greater repulsion between this? Actually, let's make it green. We have this green electron here, and the green electron here. When we look at it, which one do you think has less repulsion between the green electron and the red electrons?
Green, the first one.
The first one, because the first one is going to concentrate the red electrons into a smaller volume. Therefore, the green electrons occupy this larger volume here. Versus, if we look at the green electron, the red electrons here, they're occupying the same space, the same volume. So the repulsions here are going to be more stronger, more significant. And so when they occupy the same space, that causes repulsion, which destabilizes one of the orbitals. And so, let's see.
So how do you translate that into the other figure?
How do you translate that into this?
To the dot, yeah, that thing.
Yeah, then we have two diagrams. We have two diagrams. One diagram is for this scenario. The other diagram is for this scenario here. And so which one is it? Here I have Z greater than or equal to 8. Which one is that? The left one or the right one? The left one. Then why does the sigma 2s shrink down more? Because it's more penetrating, and the higher the Z, the more the electrons get pulled in. The weaker the Z, the less the electrons get pulled in.
The less they get pulled in,
Mm-hmm.
but they look like they got pulled in.
This is it. Let's say, there's a race, and the prize, everybody's going for the prize. And in one of the races, the prize is just a little, maybe a name tag with your name on it, that where you placed. And in the other one, there's a $1,000 prize, whoever gets it, right? And so the $1,000 prize is going to be a stronger attractive force, right? And that's going to differentiate these two more than a name tag. Some people don't really care about that. It's not a very strong attractive force, so things get bunched up more, whereas this would segregate the electrons more. And so the sigma 2s would be being pulled towards the prize more significantly than the sigma 2p.
Why is sigma 2s proportionally smaller when Z is big? Why don't they both get stretched?
Because the 2s is more penetrating than the
Means
2p.
it's closer.
It's not closer. I mean, more penetrating is, it can be closer to the nucleus than that.
Is the 2p being affected by the Z?
The 2p is going to be affected by the Z.
But it's just very little bit.
Less so. Less so. The 2p is going to be pulled in closer also. But when the Z becomes weak, when the attractive force becomes weak, then, you know, there isn't really a pull on it, right? If the attractive force, let's say this is a duck pond, you know, and there's not much food here. The attractive force isn't so strong, and so all the ducks are randomly dispersed in this pond. But if the attractive force is very strong, then, you know, some of the stronger ducks are getting pulled towards that. And so if the attractive force is strong, the sigma 2s is going to be pulled more strongly to it.
Why 8?
Hmm?
Why 8?
Why what?
Z equals 8. Why that's the threshold?
That's where it is. I mean, that's the transition. Why it has to be because of
Is
the
that a gradual
energy.
change?
Hmm? It is a gradual change, right? But the gradual change is, you know, it's enough of a jump when Z hits 8 that it pops up or pops down, you know. And so, in other words, when Z is less than 8, the attractive force isn't so strong, and so that the sigma 2s and the sigma 2pz interfere with each other. And so we have this diagram here. Why 8? 8's just what it turned out to be.
And when you draw the repulsion with the red dots,
Mm-hmm.
what is that repulsion?
What is the repulsion?
Like, what?
The repulsion is this. It's the repulsion between the electron cloud of the red dots and the electron cloud of the green dots. Both of these are negative. So you got negative and negative repulsions. Here, we got the electron cloud of the green dot and the electron cloud of the red dot. You got to imagine the electron cloud as being like fog, you know. And the fog here is in the same volume, the green and the red. Here, you know, some of the green fog can escape from the red. It gives you a little bit of breathing. And so the repulsions aren't as great. And so let's say in one instant of time, the green electrons were here, and the red electrons were here. You know, if that's the case, then are the repulsions going to be as great as if the green electron were here? No, the repulsions are going to go down because electrons are confined there. But here it's more spread out, and so you got constant repulsion, right? There's always repulsion. Even if the green was here, it's still spread out. You know, the probability density
What about
distribution.
the red electrons are out there?
That could be, but overall, over a long period of time, it's smeared out over the whole thing. And this is smeared out over the whole thing. And so it turns out that this scenario is going to yield to greater repulsions than this scenario. That's it. You know, why? You could do the calculations. You could do some physics calculations and actually calculate it. you know, overall, it's going to give you less repulsion. That's it. You know? And so, you know, you just take it as is. This is the way the orbital can get pulled in, and then if this can escape the same volume, then it turns out it's less repulsion.
And how does the repulsion affect the energy level?
Well, if there's greater repulsions, it bumps up the energy level. And so here, because of the repulsions, we bump up the energy level. And therefore, you have two diagrams you have to work with.
So you said this happens gradually, right?
No, it happens as a transition, you know, as you transition from z equals 3 to z equals 8. It's going to happen gradually. So what's going to happen is, yeah, the repulsions are going to get greater, so it's pushing the sigma 2p higher and higher, and eventually the sigma 2p flips to the other side of the pies. But we aren't showing it because we aren't showing individual diagrams. What you'd be watching is you'd be watching the sigma 2p get higher. A little higher, but it's still below. A little higher, but it's still below. A little higher, but it's still below. And then all of a sudden, pop, it's on the other side. Now it's changed the order. It happens like that, but, you know, do we have to know the distance? Do we do that calculation? We don't do any quantum mechanical calculations. And so all we do is we know, you know, there's different patterns. You know, how far below, yes, that's going to have an impact, but what has a bigger impact is how it fills. If you fill these orbitals first versus filling this orbital first, it's going to change primarily its magnetic properties, potentially. And so this is why we care about this, because all we're doing with this is we're figuring out something called the bond order. You know, what is a bond in molecular orbital theory? What is a bond? How do you define a bond in molecular orbital theory? Well, how do you define a bond in valence bond theories? They tell me that. Overlapping atomic orbitals creates what? Overlapping atomic orbitals creates greater electron density between or in the internuclear region, which the nuclei are attracted to, and that holds it together. Okay, now how do you define a bond in MO theory? What did I write down yesterday? The bond is in MO theory. More bonding electron density than
Versus
antibonding electron density. So this, you know, this, although this probably won't change that, but it's going to change where the density is distributed. Is the density distributed in pi, you know, above and below the axis, or is it distributed in a sigma? And so that brings up an interesting question here. Actually, let's see. Well, we'll look at it. And so how do we use this? How we use this is we just know that there are two diagrams. They're going to fit this pattern here. Do you see the atomic orbitals are missing? And all we see are the molecular orbitals. And so here we have a 1, 1, 2, 1, 2, 1 pattern of z less than 8. Here, you know, this is the sigma 2p. It should be down here. A sigma bonding orbital has more density right between the two nuclei than pi. And so sigma should be stronger and lower in energy. Right? But it got popped up. Why did the sigma get popped up here? Because of repulsion. Now, looking at this diagram here, we got the 1, 1, 2, 1, 2, 1 pattern. We fill it with electrons. And so this is, you know, we do MO just for diatomic, simple diatomic molecules. And so Li2 is a very bizarre species, but this would be a lithium molecule with 2 lithium atoms. And so if we form an Li2 molecule, you know, what can we say? Well, one thing we can say is each lithium has 1 electron, valence electron, so we got 2 of them. We got 2 valence electrons, so that's 2 electrons in the sigma 2s, which means this is diamagnetic, all paired, and the bond order is 1. We have 2 electrons worth of bonding electron density. 2 electrons worth of bonding density is one bond. Whereas Be2 has 4 valence electrons. We have 2 in the bonding, 2 in the antibonding, So we have two bonding, two antibonding. The antibonding cancel out the bonding and give us a bond order of 0. And so magnetic properties aren't required here because it's bond order is 0. Okay, then we go to B2. B2 has 6 total, 3 from each boron. And so we fill it. 2, 4, 5, 6. This is paramagnetic. If we use the other diagram for it, with the sigma 2p below here, would it still be paramagnetic? No, it would be diamagnetic. And so that makes a difference here. And the bond order is, well, we got in one antibonding and bonding, these cancel. That leaves us with 2 electrons in the bonding, which is a single bond, a bond order of 1. B2's got a weird bond though. Let's look at the B2. In valence bond theory, pi bonds are always accompanied by a sigma bond. Can the same also be said of molecular orbital theory for diatomic molecules? Are pi bonds always accompanied by sigma bonds? No, because here we see it. These two cancel, and that leaves us with just only pi electron density, above and below, which holds the 2 nuclei together, and in 2 planes, one in the plane, one perpendicular. And this is 1 electron's density is worth of those. And so it's bond order 1. The C2 diamagnetic bond order is 2, so we'd have a carbon-carbon double bond if we had the C2 molecule. N2 is a common, and so all these are exotic, rare, exotic. N2 is very common. N2 has a Z of 7. N2 is 5 electrons, each N, so that gives us a total of 10 electrons. So 2, 4, 6, 8, 10 electrons here. Diamagnetic because there are no unpaired electrons, and bond order, okay, this cancels this. That leaves us with 3 pairs of bonding electrons, which is a triple bond. Okay, now the diagram flips to the other one. Z is equal to 8. Z is equal to 8. The 2s and the 2p get out of each other's way. Z less than 8, the 2s and the 2p interfere with each other. And so here they're out of each other's way, therefore the 2p isn't being bumped up in energy. The 2p is in its normal, regular position. And so O2, did we do this one already? I drew the dots on the board. The dots on the board, I know that it was crazy, but the thing is, you have to do it yourself. If you do it yourself, then it'll make a lot more sense. Rather than deconvoluting my mess. And so you make it, and then you see how it's made, and then it should be a lot easier to visualize. But what we see is here, it's paramagnetic. Each oxygen is 6, so there's a total of 12 electrons here. Paramagnetic, in the bond order, okay, these cancel this. We got 2 antibonding, that'll cancel 2 of those. And we end up with 2 pairs of bonding, which is a bond order of 2. The equation for this, the bond order, is the number of bonding electrons minus the number of antibonding electrons divided by 2, because 2 electrons define a bond. So that's O2, and you can see the electron density is different than what you get in valence bond, because we have these unpaired electrons in the P. One of the P's in the plane, the other P perpendicular to the plane. Then we go to F2. F2 is bond order 1, diamagnetic. And then Ne2. Ne2, all the antibonding cancel out the bonding, and we get a bond order of 0. So Ne2 is not predicted to exist. Therefore, we aren't going to have any magnetic properties. And so those are all the simple diatomics. This is how your book's homework is going to show the MO diagram, but the reason they do this is to save space. It's not because this is the best way to do it. The best way to show it is like this. And the situation with your book is it doesn't have enough room to show it like this. And so that's why. On a test, you would show it like this. Okay, this is O2. You know. We talked about O2 already, but we can also do other types of questions like O2 plus. If we knock an electron off O2, does that make the bond stronger or weaker? It makes it stronger because if we knock an electron off, we're removing a anti-bonding electron. If we remove that, then that should help strengthen the bond. O2 plus is not stable though. O2 plus is highly reactive. We're just talking about the bond, the oxygen-oxygen bond strength, not necessarily the stability, because O2 plus will be a powerful oxidizer, much more powerful than on the chart there because it really wants an electron. We could look at other species too. You know, in addition to O2 plus, we can look at O2 minus. Would O2 minus be better or worse? Worse, because that extra electron would go into a antibonding. And then O2 2 minus. O2 minus, have you ever heard of this stuff? O2 with a minus charge? No. O2 plus is rare, O2 minus isn't. O2 minus is common, it's called superoxide. And then O2 2 minus is common also. Do you know what that's called? Peroxide. So superoxide and peroxide. Okay, those are the simple diatomics. Now we're going to look at a little bit more complicated one, the heteronuclear diatomics, and we're going to look at carbon monoxide. Carbon monoxide is not easy. The reason carbon monoxide is not easy is because carbon is less than 8, oxygen is equal to 8. So which diagram do we use? Do we use carbon's diagram or oxygen's diagram? And so let's take a look at this diagram. Look at the pattern of the MO. What does this resemble? Ignore the labeling scheme. But what does this resemble? Carbon's MO or oxygen's MO diagram? Oxygen? Look again. Which pattern does this represent? Okay, we normally think sigma. This looks a little different because oxygen is more electronegative, so it pulls down these energies, makes them smaller than carbon. You know, in other words, oxygen has a higher Z effective than carbon. But looking at the orbitals, this would be sigma 2s followed by sigma star 2s, and then we go to the pi's. So going from sigma star 2s to the pi's rather than sigma 2p means that we're dealing with carbon. And so if we have a heteronuclear, which diagram do we use? Do we use carbons or oxygens? We're using carbons for carbon monoxide. But can we come up with a simple rule? No, not always, because things are more complicated. In fact, here you can see that life gets more complicated because there's more mixing going on than what I showed you. Do you see all the dotted lines? Here. See, here we normally go here and here. You know, the sigma star, here, and the sigma. But take a look at what else is happening. There's some 2p getting mixed in here too. And so there's more mixing going on here than what we showed. Well, anyway, carbon monoxide has 10 electrons. You know, 4 from carbon, 6 from oxygen. That gives us 10 electrons. Carbon monoxide should be diamagnetic, and the bond order should be, if the antibonding cancel the bond order is 3. 3 pairs of electron density. And so this diagram you have to compare with the other diagram that we saw earlier. Do you see? It's the 1, 1, 2, 1, 2, 1 pattern versus this pattern here. This pattern has a symmetry. You know, you knock off the 2s. Do you see the symmetry? The 1, 2, 2, 1 for the p's. The p's don't have that symmetry. They have a different kind of symmetry here. All right, that's carbon monoxide. And so we could look at some others, like cyanide. If we look at cyanide, which one do we use? Less than 8 or equal to or greater than 8? Less than 8. Carbon's less than 8, nitrogen's less than 8. So this one's easy. We just go less than 8. So let's take a look at that. If we go less than 8, carbon monoxide has how many electrons? Well, not carbon, we just did carbon monoxide. Cyanide. Cyanide has 4 electrons from carbon, 5 electrons from nitrogen, and a negative charge means 1 extra electron. So it's 10 electrons. And so it'd be something like this. 10, yeah. It'd be the exact same diagram as N2. Carbon cyanide would have 10 electrons. So we fill 2, 4, 6, 8, 10. And then we look, what's the bond order? These antibonding cancel these bonding. That leaves us with 3 pairs of bonding electron density. Bond order is 3. Diamagnetic. And so cyanide is diamagnetic, bond order 3. So bond order 3, triple bonds, and paramagnetic somewhere. All right, that's MO theory, but that's MO theory restricted to diatomics. We don't really do MO theory for anything more complicated than diatomics because it gets very complicated. And so what we're going to do instead is we're just going to look at some examples of things that are more complicated than diatomics. And the first one is benzene. Benzene C6H6. We look at the bonding of benzene. If we look at the Lewis structures for benzene, we come up with these 2 resonance forms here. What's the hybridization on carbon? sp2. So can you see the sp2 orbitals? Where would the p orbitals be? P orbitals would be perpendicular. And so all these are sp2, so it's flat. This is a shorthand way of representing benzene, where it just shows the carbon-carbon bonds. And it omits the carbon-hydrogen bond. And so we see the 2 resonance forms here. It turns out, though, that the best structure would be the resonance hybrid. Because what we see is that the pi electrons are not localized, but the pi electrons are actually delocalized. And so what I'm going to do is I'm going to just tilt this up a little bit so we can see it better. But basically, I'm going to draw this hexagon to represent benzene here, showing the bonds. Each of those carbons is sp2. And so that means that the p orbitals, this is side view here. P orbitals are all sticking up like this. If I look at one of the resonance forms, let's look at this one here. I see a double bond here, here, and here. And so what I can do is I could just go ahead and do that. I can make a double bond here, right, overlapping these. I can make a double bond here and here. And so what I have is I have the pi electrons localized here, here, and here for 3 double bonds, right? Then we have the other resonance form. The other resonance form is just putting pi electrons here, moving them here, and moving them here. But we know that, you know, electron density is like a fog, and this fog is it going to want to localize? It'll localize if there's a wall here, but is there a wall here separating? No. And so what happens with benzene is we delocalize all the pi electrons over all the bonds here. And the same thing here. And so it turns out that all the bonds are exactly the same with one another. The bond order is 1.5. Right? But 1.5 bond order means it's between a single bond and a double bond in terms of strength. But this is actually more. This is actually more stable than expected. The reason it's more stable than expected is because this delocalization, this delocalization over the pi bonding network helps increase the stability of this structure. And so we can see it here. See all the p orbitals are lined up. And so if we smear out the electron cloud over all these, it becomes quite a bit more stable. This is pi bonding network. This would be the sigma bonding, where the purples are what orbitals? sp2. So we see the sp2 sigma bonding. These electrons here are localized. They aren't being spread out over the entire structure. These electrons here are delocalized. This is the common symbolic representation to show that delocalization of the electron cloud. And we give a special name to this type of compound. In organic chemistry, they call these aromatic. They're aromatic because they have additional stability due to the alternating double bond network. When you have alternating double, single, then what's going to happen is these are all sp2, and all the p orbitals will line up like this. And so when all the p orbitals line up like this, you can spread out the electron cloud over all the p orbitals. All right, this is with valence bond theory. So with valence bond theory, we come up with this, the hybrid structure, etc. In MO, you don't have to do any of that. In MO, the MOs are a bit more complicated. So we do all these additions, with LCAs, with atomic orbitals. We come up with these MOs here. But when you look at the MOs are naturally delocalized. This is just one orbital. One orbital holds 2 electrons. These 2 electrons are spread out over the entire structure. Here it's more localized. Here it's more delocalized. And so we add all these up, and this is essentially what we get for the pi bonding network. It's going to look like a resonance hybrid here that we had, and the pi bonding electrons are spread out above and below. Okay. And so this would be the molecular orbital representation of pi bonding in benzene. These are computed pi molecular orbitals. Benzene. Okay, let's do more about delocalization. In organic chemistry, the more resonance forms you draw, the more places the electron can go. The more places the electron can go, then the more delocalized the electron density is, and the more stable it becomes. And so there's a simple rule in organic chemistry. The more resonance forms, the more stable. Okay, when we look at this ozone, ozone has the alternating, double, single here. But ozone is a bit tricky because if you look at this, oxygen is what hybridization here? sp2. This oxygen is, and this oxygen is sp3. And so it looks like what happens is, as we rearrange electrons, so if we put these electrons down here, that pops these electrons out. When we pop these electrons here, it changes this from sp3 hybridization to sp2. And when we pop the pi bonding electrons out and put it on this oxygen, it switches this one from sp2 to sp3. And so let's take a look at just the left resonance form here. If we look at the left resonance form, this is what we end up with. So, actually, how should I draw this? Draw this like this. Let me draw it with the orbitals. Okay, this is sp2. It's carbon. Not carbon, oxygen. The left oxygen is sp2. Here. So we have an sp2 sigma bond. And then we're going to have a pp pi bond. PP pi bond's localized here. And so we got the p orbital. We're looking at the top view. So we got the pp pi bond here. It's localized on the left. Yeah. Then we got a lone pair. A lone pair here, here, here. This other sp2 lobe is going to bond to an sp3 oxygen here. Two in the plane, one coming out, one going in. So this is sp3. We've got 3 lone pairs on this one. Like that. And so this would be the structure, right? Now, how am I going to delocalize it? You know, on benzene it was easy to delocalize because I had a p orbital here, a p orbital here, and a p orbital here, but I don't have a p orbital here. And so when I delocalize this in the valence bond picture, you know, it can't spread out here because I can't give this more electron density, right? And that's this is why, remember I said, you know, some people were asking, I think in this class, or maybe it was the other class, some people were asking, you know, how do you determine the hybridization of the atoms in the hybrid resonance structure? You know, the hybrid resonance structure? How do you determine it? Well, it's not so easy to do. And so, oops. So this is how it's done. Because in the other structure, it just flips, right? This one, what we got is this sp3 lone pair goes in here, and it pops out the pi bonding electrons out here into a lone pair. And so this one switches to sp3, this one switches to sp2. And so it's got to resonate back and forth, doesn't it? In the hybrid. Otherwise, you know, we can't really spread the electron density out this way, can we? And so it looks like it's impossible to spread the electron density out like we did in benzene, but it turns out it's not. It's not because we expect it to be, we expect sp3, you know. Why do we expect sp3? Why do things hybridize? Why do we form hybrid orbitals? Stable? Stable. Why would it be more stable? Well, we don't necessarily have to hybridize for more bonds. That's why I split it. I split it into 2 versus what Petrucci did. Petrucci did it in 1 step. But we don't have to hybridize to necessarily make more bonds. We hybridize primarily to, I said for big atoms is hybridization is critical for big atoms. Why? Yeah, we hybridize to minimize repulsions. If you got gigantic p orbitals, then the repulsions aren't going to be so big, right? Because there's lots of space compared to very small p orbitals. Very small p orbitals concentrates the electron cloud right against the nucleus, and you get significant repulsions there. Very big p orbitals spreads it out in space. And so we hybridize to minimize repulsions. Right? And so if we have 4 groups of electrons, we're going to hybridize this sp3 so that it adopts what kind of geometry? A tetrahedral type electron geometry to minimize the repulsions, right? What if we didn't hybridize this sp3? What if we hybridize this sp2? it would be trigonal planar. And so let's look at this one again and hybridize it sp2. Well, if we hybridize it sp2, it doesn't seem like that's such a great idea, because the bond's okay here. We got the bond. And we got the two lone pairs and the sp2s like this. But where does the third lone pair go? The two lone pairs are good here, but the third lone pair is going to be in a p orbital, and the p orbital is at a 90 angle. And the 90 angle is not favorable, right? It's better to go 109, correct, for minimizing repulsions. And so this isn't so good initially, but it could be good. You know, there's going to be a little cost because you're going to increase the repulsions, but you might get some benefit. Where would the benefit come in, if any? And so let's look at the other orbitals here. So this is sp2, right? And this is sp2. So now all the oxygens are sp2. Then we have this pp pi bond here. And we have this sp2, sp2 sigma bond here. Two lone pairs here. How could this be good? How this could be good? Why would this go sp2 hybridization? It'd go sp2 hybridization to spread out the electron cloud. Because now look, I have these three p orbitals all perpendicular to the plane, and therefore the electron density, like a cloud or fog, can spread out. And so in other words, rather than localizing this lone pair here, we can partially delocalize it into the rest of the structure. And the more we delocalize or spread it out, the more stable it is. And so it doesn't make sense when we look at this. You know, this is an sp3 oxygen, isn't it? This is an sp3 oxygen. But it's going to hybridize sp2 because there's a secret advantage. The secret advantage is that we could get this pp overlap, which is going to delocalize the electron density through more of the structure. Spread it out. Does that make sense? Maybe, maybe not. Well, anyway, look at this. We don't have to do this in MO. In MO theory, look at, this is the delocalized pi molecular orbital that you get from MO theory. Did we have to talk about this thing where it doesn't hybridize sp3, it's going to hybridize sp2, that way we can get all the p orbitals line up like that? No, MO, it's direct. So MO, what did we call MO? What's the difference between MO and valence bond? Lots, but tell me one of the key.
The structure.
Well, it's going to give slightly different structure. So, I mean, the structure in terms of electron cloud density. Well, what would you say the key difference between MO and valence bond is? MO is more accurate. MO is more difficult. MO is, well, is it? Yeah, it's more accurate, but what's even more accurate than MO? Quantum mechanics is more accurate than MO? MO is quantum mechanics. MO is the full quantum mechanical approach to molecules. The valence bond is the light version. And so you have to come up with ways. You know, that's one. This is. Let me tell you, that's what I did when I was looking at valence bond. What's the difference between valence bond and MO? You know, is Petrucci going to say that MO is the full quantum mechanical and valence bond is the light version? No, but he's going to say something. And so what you do is you take what he says, and then rather than repeating what he says, you think of what makes sense to you, and that makes it more memorable. Because I could have just repeated what Petrucci said. What is the difference between MO and valence bond? But it doesn't stick. In fact, I forgot what he said completely because I've read it. No, totally forgotten it because it just didn't stick. The reason it didn't stick is because it wasn't in my words. It's much easier to come up with your own words than remembering someone else's words. But anyway, going back to this, let's read this. Petrucci doesn't hybridize the oxygen, the terminal one. But anyway, with Vesper's theory, we predict trigonal planar electron group geometry. Yes, sp2. It's trigonal planar group geometry, it's bent molecular geometry. The hybridization scheme chosen for the central oxygen is sp2. And although we normally do not need to invoke hybridization for terminal atoms, this case is simplified if we assume sp2 hybridization for the terminal oxygens as well. And so he's going to assume sp2 and sp2. This one I would have automatically gone to sp3. Thus, each oxygen uses the orbital set sp2p. So sp2, 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 p, p, p. And then you got the three aligned p. Orbitals. In other words, we get this situation. This is top view, but we could look at that side view as well. The side view is going to look something like, actually this, it's going to look something like this, right here, the side view. Oops. Okay. We don't have to do any of this, as I said, for MO. And so these are generating the molecular orbitals. If you look at molecular orbitals are naturally delocalized. Those two electrons aren't localized within two bonds. Two atoms here. It's delocalized over the three atoms. And so these are the molecular orbitals that are generated. When you take three molecular orbitals and do an LCAO, then with three MOs, we get one bonding, one anti-bonding, and the third one becomes a non-bonding MO. And so there are three types of MOs, the bonding, the anti-bonding, and the non-bonding. About that. Okay, let's take a look at nitrate. What's the hybridization on nitrogen? sp2. This oxygen, sp3. This oxygen, sp3. But we have three resonance forms, right? And the pi bonding electrons are delocalized over all three oxygens, all three nitrogen-oxygen bonds. And so the best thing to do for this is to say, I'm not going to hybridize that sp3. sp3 would give you the minimum repulsion. Instead, we're going to hybridize these oxygens as sp2, and then put a lone pair in the p orbital. The p orbital is perpendicular. Now, if all these are sp2, then take a look. All the p orbitals line up. When all the p orbitals line up, then we can spread out all the pi bonding electron density over the entire ion. And so that gives us our hybrid structure. This is going to be all sp2. I drew it differently because I drew little dash here, right? Little dashes here, little dashes here, little dashes here, to show that there's going to be two lone pairs that are going to be spread out, right? But those dashes are actually going to go in the p orbital here, p orbital here, p orbital here, as well as the pi bonding electrons here. And so this is what it looks like here. If we were to do it all, the p orbitals here, 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 and here all line up, so that way we can smear out the electron cloud over the entire ion. We don't have to do that in molecular orbital. In fact, this is the molecular orbital for that. And so molecular orbital mimics what we would have gotten for the resonance hybrid. Resonance hybrid. Okay, so these are looking at the MOs. So we can see that here, when we have alternating double, single, double, single, double, single, this is aromatics. Aromatics are going to have unusual stability because of what? All the p orbitals are all lined up, right? Which means all the pi bonding electron density is delocalized over this entire thing. So we have that there. This is beta carotene. If we look at this, though, we have the same thing here, the pi bonding. But what about this? If I look at the pi bond here, can these pi bonding electrons smear out over the rest of the structure? No. These ones are localized here. Is the p orbital is terminated. This turns out to be sp3 carbon. We aren't going to hybridize it to sp2 because there are two hydrogens attached here, which aren't shown. This is another sp3. And so this is isolated. So this pi bond is localized. These are delocalized. What about this one? Localized. It's having that delocalized pi bonding network that creates the aromatic. All right, that's some stuff on hybrids and MO, and more complicated structures. Let's take a look at quickly at bonding in metals. You know, when we take here's an atomic orbital. When we combine two atomic orbitals, we get two MOs, bonding and anti-bonding. If we take three atomic orbitals, we get three MOs, bonding, non-bonding, anti-bonding. Four MOs gives us two bonding, two anti-bonding, four AOs. Five AOs gives us two bonding, two anti-bonding, one non-bonding. 6 AOs, atomic orbitals, gives us this. 16 will give us 8 bonding, 8 anti-bonding. And so if we go to Avogadro's number, then we'll get an Avogadro's number's worth of bonding and anti-bonding orbitals. And so that brings us to metals. Metals, we have the electron C model, or we have band theory. What band theory is you have bands of MOs. If I have an Avogadro's numbers worth of lithiums and I'm doing LCAO, then I'm going to get Avogadro's numbers worth of orbitals. And when I look at the orbitals here, we have bonding MOs and anti-bonding MOs. In other words, bonding band of MOs and an anti-bonding band of MOs. In band theory, we call the bonding band the valence band. And the anti-bonding we call the conduction band. So we got a valence band, conduction band. In insulators, we got a big band gap here. You know, you need UV light or X-ray light to pop an electron from this set of MOs to this. This is the spectroscopy part. In the spectroscopy part, valence bond doesn't use this to us. In semiconductors, the band gap is visible light. And so semiconductors are colored, visible light hits here. And not only does visible light hit here, when visible light hits here, it promotes an electron up here. When an electron gets promoted here, the electron's totally delocalized. That electron's free to move. And so when we shine light on semiconductors, they start to conduct electricity. In metals naturally conduct electricity. That's because the jump here is so small. It's thermal energy, just room temperature is enough to knock electrons in the empty orbital here. The empty orbital's the electron's free to move. And so conducts electricity quite well. And so here we see an overlap between the bonding MOs and the anti-bonding MOs, the band of them. Here, sometimes the bonding MOs aren't completely filled. And so we have half filled, what we call valence band. This is going to conduct electricity as well. This band theory stuff is talked about in Chem 1B in more detail, but I thought I'd just briefly mention it here. So I'm going to skip the other parts of this. I think that they talked about this already. Yeah. Okay, those are some of the basic concepts for this, and a few advanced concepts, but not all of them. What I want to do next is I want to put this into some practice, this structural analysis. And so we're jumping to chapter 16. 16.1 is Arrhenius Arrhenius acid is just H plus AQ, anything that gives H plus AQ. You could read this as a half a page. 16.2 is Bronsted. Bronsted, proton donor, proton acceptor. This is a half a page worth. It's a half a page worth up to here. Yeah, and so this K calculation, we don't bother. K calculations are in Chem 1B. And then we jump to 16.8. 16.8 is molecular structure and acid-base behavior. 16.9 is Lewis. I already talked about Lewis acid bases, electron pair donor, electron pair acceptor. And so what I want to do is I want to talk about molecular structure and acid and base strength. And so let me write down a couple of things here so we're not out of sync. And so acid strength. Acid strength, the most important factor in acid strength is the bond strength. And it's the HB bond, where B is just the rest of the acid. The weaker the bond, the stronger the acid. So the weaker the bond, the stronger the acid. The next factor is bond polarity. The more polar the bond, increasing delta plus increases the acid strength. Okay. The next factor is the stability of the conjugate base. The stability, there are two major factors here, and that is charge delocalization by induction. Induction is just something sucking off the negative charge density, or by resonance delocalization. Resonance delocalization is by far more important. And the stability of the conjugate base also has solvation / hydration effects, which we'll talk about later. And so let's take a look at, oops, I'm just going to erase that. I'm just going to look at it in the figure here. Let's look at HF versus HCl versus HBr versus HI. HI has the weakest bond. HF has the strongest bond. We know that HI, if we look at iodine, what's the hybridization on iodine? What's the hybridization on iodine? It's sp3. Iodine's a big atom, so do we really need to hybridize it? Probably not, but to make your life easier, why not? Just go ahead and hybridize. Hydrogen is S. If you look at the electron cloud is smeared out over a pretty big volume versus fluorine. Fluorine is what, smaller? Fluorine is, what's the hybridization of fluorine? sp3. Hydrogen is S. And so when we look at the electron cloud here, the electron cloud is concentrated here. Here it's very low density. So which bond is easier to break? Iodine. The HI bond is much easier to break than the HF bond. And so that's it. But there's another thing. The other thing is polarity. Which one is more polar? Well, hydrogen. HI isn't very polar. And so here, if you're a base like water, water is polar, it has a delta minus. Which one are you going to be more attracted to? HF or HI? HF. HF is going to be a stronger attraction because it's more positive, right? And so water comes along and tries to pull off the proton. Water gets into tug of war with fluorine. Who's going to win? Water is in a tug of war with fluorine to pull off that proton. Who wins? Fluorine. Why? Because the bond is too strong. Water gets in a tug of war with iodine. You know who wins? Water. Water is going to pluck. And so even though water is not as attracted, it's just easier to remove because the bond is weak. And therefore, this is the trend. The most important factor is not polarity because yes, it's more attracted, but it's too hard to pull. And so the most important factor is bond strength. And so in terms of acid, the strongest acid is HI. The weakest acid is HF. But it turns out HF is unusually weak, a lot weaker than you'd expect. And the reason why, when you look at these numbers, these are the numbers for the strength. This is 10 to the 9. HCl is 10 to the 6 in terms of strength. HF is 10 to the minus 4, so that's like 10 billion times weaker. It doesn't have 10 billion times weaker bond. What happens is HF doesn't, fluorine, even if, let's say it was their success, H plus got pulled off of fluoride. Unfortunately, fluoride doesn't let go. There's going to be an ion-ion attraction here. It's not a bond, it's an inter-ionic attraction, which prevents the H plus from leaving completely. Once you break the H plus from I, it's gone. It's gone. There's too weak of a pull. But fluoride still has that pull. It doesn't let go. And so you need additional. And so this weakens HF as an acid that fluoride won't let go. Okay. We'll talk more about this later. But that's the only one. And then we'll look at the other factors next time. Yeah. Sorry.
So this chapter 16 chapter.
Just this first part of chapter 16. First part of chapter 16 are this group of acids.
You said it was going to be on the final. You said 9, 10, or 11 for the next test, and then 12, 13, 16 for the final.
I know I said that, but
You changed your mind?
I changed my mind because I got through some of 16
So in
today.
the book, what is going to be in chapter 16 on this test?
Acid base, Arrhenius, 16-8.
The definition of Arrhenius. Arrhenius is
H.
H plus. Definition of Bronsted, proton donor. Definition for Lewis, proton.
Acceptor.
Not proton, electron pair. That's it. And then this, the binary acid. Why is HI a stronger bond than HCl? Because it has a
Bigger radius.
weaker bond. Why does it have a weaker bond?
Bigger radius.
Bigger radius. Why does a bigger radius make a weaker bond? Because the big orbital here,
Low electron.
yeah, less electrons density. That's it for chapter 16. But there's going to be more of chapter 16 though later.
So you mentioned the more polarity, the strength, the stronger the acid of strength,
Yes.
but the HF has a more polarity, but it's weaker acid.
Yeah. So there's a conflict. The conflict is polarity says HF wins. Bond strength says HI wins. Experiment says HI won. And so which one's more important, polarity or bond strength? Bond strength. So bond strength overrules polarity. And so I try to show that by, the base, in this case, water, is going to be more attracted to HF. But it's going to have a hard time breaking this bond.